Today we're going to be covering the first part of chapter 16, and it's going to talk about carbohydrates, and we're going to learn how to do Fisher projections and Hayworth projections. This might be new for some of you, so feel free to pause the video as you go along. So my objectives for this chapter are for you to be able to draw and interpret Fisher projections for some of the common monosaccharides that we'll be discussing, and also to be able to convert between a Fisher and a Hayworth projection. What is a carbohydrate? A polyhydroxyaldehyde, aldose, or a polyhydroxy ketone, or ketose, or a substance that can give these compounds on hydrolysis. So what do I mean by polyhydroxy? You see you have multiple OH groups, so that's your polyhydroxy, and then this is an aldehyde. Here, polyhydroxy, and this is a ketone. So this is basically the chemical structure of what carbohydrates are. We know that monosaccharides are the building blocks of all carbohydrates, and in general they have this formula CnH2nOn, where N varies somewhere between 3 and 8. And as I said before, an aldose is a monosaccharide that has an aldehyde group that I showed you earlier, and a ketose is a monosaccharide that has a ketone group. Monosaccharides are classified by the number of carbons they have. The simplest form is a triose, which is 3 carbons, and then they go up from there. So glyceraldehyde here is a triose, and it has one stereocenter, which is that center carbon. And so therefore you can have 2 stereoisomers called enantiomers because they're mirror images of each other. So what's a stereocenter? A stereocenter is an atom, typically a carbon, that has 4 attachments that are unique from each other. Since each attachment is unique, if we move any 2 attachments to another position, then we would form a new molecule. Fisher projections are a way to represent these carbohydrates in a form that's 2-dimensional, even though the molecule is 3-dimensional. And what you see here are that the lines that represent bonds projecting forward are horizontal, and the vertical lines represent bonds projecting to the rear. And typically when you draw these out, you're not going to draw that carbon at the intersection of the horizontal and vertical lines. So I actually have a couple videos on Converge for you to watch that go into great detail on how to draw Fisher projections. Fisher projections were proposed by a German scientist whose name was Emil Fischer. And according to his model, when the OH or hydroxyl group is on the penultimate carbon is on the right, that would be a D monosaccharide. When the hydroxyl group is on the left on the penultimate carbon, that would be an L monosaccharide. And what do I mean by penultimate? So this one has 6 carbons, and number 5 would be the penultimate, meaning it's next to last. So we saw before with glyceraldehyde that stereoisomers that are mirror images of each other are called enantiomers. Now we're moving on to tetroses. And what you see here is that we do have stereoisomers, but they wouldn't be mirror images of each other. So these two, D-erythrose and D-threose, are called diastereomers. Epimers are diastereomers that differ only in one chiral carbon, and these two would be epimers of each other. We can have enantiomers in these 4-carbon aldotetroses. And what I want you to see here is that we have this mirror plane. And what you see is that D and L erythrose are mirror images of each other. And again, we see this mirror plane occurring, and D and L threose are mirror images of each other. So those would be considered enantiomers. You can actually predict the number of stereoisomers you have if you know the number of stereocenters you have. So if you see here, D-glyceraldehyde, there's going to be 2 stereoisomers, the D and the L form, because there's 1 stereocenter. With your tetroses, you're going to have 2 stereocenters, right here and here. So therefore 2 to the 2 is 4, and you'll have 4 stereoisomers. Moving down, you have 3 stereocenters, and therefore 2 to the 3 is 8, and you have 8 stereoisomers. And that keeps going so on and so forth. What happens if a sugar forms a cyclic molecule? We see cyclization of sugars quite often once they are long enough, and this is due to an interaction between functional groups on distant carbons. So when C1 and C5 interact, they make a hemiacetal here. So what you have is the alcohol and the aldehyde group interacting to form a hemiacetal. Cyclization using the C2 and the C5 here can result in a hemiketal formation. And in both cases, because of that cyclization, the carbonyl carbon is now a new chiral center, and we call this the anomeric carbon. What you find that monosaccharides that have the alcohol and the aldehyde groups in the same molecule typically exist as 5 or 6 membered cyclic hemiacetals. So what is the anomeric carbon? It's a new stereocenter that is caused by the cyclization. And what are anomers? They're carbohydrates that differ only in their anomeric carbon. Let me explain this in more detail as we look at 3 different forms of glucose. What you see in the middle is the open chain form, and it is going to be converted into either the alpha or beta cyclic form. So alpha is here on the left, and what you see is that the hydroxy group is to the right. Beta is on the right, and you see that the hydroxy group is on the left. So when we look at the cyclic forms, we see that we get a new hydroxy group forming at that first carbon. That's now a new stereocenter, and we can either have the alpha configuration or the beta configuration. So I have another video for you to watch, and basically what it does is it shows you how to convert between a Fisher projection and a Hayworth projection. A Hayworth projection is either a 5 or 6 membered hemiacetal ring that's represented either as a planar, pentagon, or hexagon. And we see these designations beta and alpha again. Basically what we see is that the alpha is going to have that hydroxy group on the bottom, or what we're saying here is in trans position compared to this group. And the beta is going to have the hydroxy group on the top, or in cis position compared to this group. And again, let me remind you that I have a video that goes and explains how to transition from a Fisher to a Hayworth projection that you really need to watch to be able to understand this better. When referring to Hayworth projections, we call these 6-membered rings pyrenosis, and we call these 5-membered rings furanosis. And the 5-member rings are really close to being planar, so Hayworth projections are pretty accurate in representing these furanoses. For pyrenosis, the 6-member ring would be more accurately represented by the chair conformation, and you guys probably did some of this in organic chemistry. But here we're going to either use Hayworth projections or the Fisher projections. Here you see a comparison between the cyclic form of the Fisher projection and the complete Hayworth projection. And then also, if you'll note that for an abbreviated Hayworth, we actually don't include the lines or the bonds for the hydrogens. So you can draw them out in any of these conformations. So today's presentation was brief because I'm asking you to supplement it with those 2 videos, one how to draw Fisher projections and the other Fisher to Hayworth tutorial. Also, you need to have Chapter 16 reading review done by Friday, and I want you to start your homework because it will be due on Monday, April 6th. You can actually do numbers 1 through 9 just by finishing today's presentation and watching those other videos, and then 10 and on are going to require the rest of the material from Chapter 16.